So here we are in chapter 4. Now this won't be on test 1, this will be on test 2. But in chapter 4 we're talking about the study of chemical reactions, and we'll get into our first reaction of a free radical type process. And as we have said before, we have the one type of arrow where both electrons are in the bond are going one direction, so we draw the double-headed arrow. And if that bond broke, we'd have an X minus and a Y plus for it. And it's a heterolytic bond cleavage where the electrons go all the electrons go one direction. Okay. In the homolytic bond cleavage, one electron goes one way and one electron goes the other way. So you get two radicals out of it with one electron on them both. And in this, we have to be careful what type of arrow we show, because the arrowhead tells us all about what's going on. So a double-headed arrow like this one, it's saying two electrons are moving. The fishhook here, in the one on the right, it's saying there's only one electron moving, so we have to be careful what we show with that. So if we calculate the formal charge on these things, to calculate the formal charge on a carbon, okay, remember we take the number of electrons assigned to it from the periodic table, so it's always 4. So in the first one, it's 4 minus 3 plus 0, 3 bonds, no lone pairs. So this one is a +1 charge. The second one is 4 minus a 3 plus 2, 3 bonds, 1 lone pair, 2 electrons in that 1 lone pair. So that's a 4 minus 5, or a -1. Then the third one across, the radical is 4 minus a 3 plus 1, which is 4 is a 0, 4 minus 4. So a radical always has no charge. And then the last one, the carbene, is 4 minus 2 plus 2, because you have 2 bonds and 1 lone pair, 2 electrons. So 4 minus 4 gives us a 0 for it. So these two over here on the right, the carbene and the radical, always have no formal charge. They will be neutral. They're very reactive because they have the electrons on that atom, but they are no formal charge. So you have to be careful about that. So make sure you know what type of arrow you're trying to show. Is it a fishhook, or is it a double-headed arrow? Okay, with a double-headed arrow, you're moving 2 electrons. With a fishhook, you're using 1. So be careful about that. And there will be the vast majority of the reactions we do and of the arrows we draw will be a double-headed arrow. We'll only do a few of the reactions where we have a fishhook arrow. Okay, so don't try to use a fishhook in everything. We'll only use it a few times. So predict the order of stability of the following intermediates and explain why. If we think about this carbon right here, if these were just 3 methyls, there would be 8 times 3, or 24 electrons around that cation. But if we look at the methyl cation here, this one would only have 6 electrons around it. So with the positive charge, the more electrons around it, the more stable it's going to be. So this is going to be most stable, with the methyl cation least stable because there are fewer electrons around it. The anion is just going to be the opposite, because you don't want a lot of electron density around it. And actually the anion with the methyl slowly reacts with moisture in the air, whereas the T-butyl, if these were all methyls, the T-butyl anion, T-butyl lithium, when it comes in contact with the moisture in the air, it spontaneously combusts. So it's much more reactive. So you want fewer electrons around the carbon with the anion. the radical, we have to decide, is that carbon, the carbon with the radical, electron rich or electron poor? Okay, so when we think about it, we know it doesn't have a formal charge on it, but that's not telling us is it electron rich or electron poor. That carbon has only 7 electrons around it, 2 to each of the 3 alkyl bonds, and then the radical. So a radical is electron poor because it only has the 7 electrons around it, so it's going to be, its reactivity is going to be similar to the cation. So the more substituted the radical, the better off it will be, the more stable it will be. So with radicals and resonance structures, since we only have 1 electron, we're moving 1 electron at a time. So in this allyl radical, we have to move 3 electrons. 2 of them come from the pi bond and 1 from the radical, so we're going to have to show 3 arrows. So the radical goes down to start forming the double bond breaks, sending an electron over to form the double bond, new double bond, and then the double bond, the other electron in the pi bond sends its electron down to form the radical. Okay, so we always will be showing 3 fishhook arrows when we draw a resonance structure of a free radical. So here on the benzyl radical, we're going to take the radical down to start forming the double bond breaks next to it, sending electrons over, and then this goes. So this is going to give us, we just formed a double bond there in the radical, and the other 2 pi bonds didn't change, and then we just keep going 1 electron at a time around the ring. And we get the radical there, and the same thing, form a bond, break a bond. Be careful how you show the arrows, where they go. Okay, they either go to the carbon atom or they go to the bond between the 2, depending on what we're trying to show. And then we do the last one here, sending electrons back to the, or the electron back to the methyl, so we have the benzyl radical. Okay, so why is this radical on that methyl so much more stable than the other? It's stable because we can draw resonance. And anytime we can draw resonance structures, the radical, the anion, the cation is going to be much more stable than the one we can't draw resonance structures for. Okay, so there are 6 steps that we can draw in a free radical reaction. These are the only 6 steps we can have. The first one always happens. It's the homolytic cleavage. It's the initiation of the step where the free radical is formed. So there is a bond that will homolytically split with 1 electron going each way. And in a free radical process, the reactions are normally started by a bond that homolytically cleaves, forming the exact same species from in each 2 of the exact same thing as that bond breaks. So in this one, we get 2 bromine free radicals. Now, not all of the bromine in this solution splits apart, just some of them. So we get a small amount of the bromine free radical, which gets the reaction going. Okay, so that's number 1. We always start the reaction with the homolytic cleavage. The second thing is going to be the addition to a double bond, or the addition to a pi bond. So the radical is going to form a bond by attacking one end of a pi bond, sending the new radical to the other end. So steps 2, 3, 4, and 5 are what's known as propagation steps. And a propagation step is where we take something and we form a new one of it, just like when you propagate a plant. Take a cutting off a plant, stick it in dirt, and it grows a new one. You've propagated the plant. Here, we've taken a radical and we've propagated it by forming a new radical. So in the first one, the addition to a pi bond, we add it in and we break the pi bond. We get a new radical on one end, and the bromine adding to the other end. Okay, we can do a hydrogen abstraction where the bromine radical goes and abstracts a hydrogen off of a carbon to form a new radical along with a small whole molecule, HBr in this case. The third one is a halogenation or halogen abstraction where that methyl radical we formed goes and grabs a bromine from Br2, and that gives us methyl bromide along with a new bromine radical. So we start with one radical, the methyl radical, we end up with a bromine radical out of the reaction. And then the fourth propagation step, the fifth step overall, is an elimination step. Now all of these won't happen, and in the elimination, it's just the opposite of the addition to a pi bond. The radical falls apart to form a pi bond, and the bromine gets kicked off as a bromine radical. Okay, and those four steps are the only things we can do as a propagation to a free radical. Okay, don't try to get fancy with it. It's going to be one of those four steps. And the last one is a coupling or a termination. So the first step is the initiation. The last step is a termination. Okay. Every free radical process will start with an initiation and end with a termination. In the termination, two free radicals come together to form a small whole molecule and kill off the free radical process. So the initiation starts the process, the termination kills it off. Okay, and these two steps are very small amount of the compound actually undergoes either of these steps, because there's not much of the free radical around, so it's hard for two free radicals to run into each other here. So here we have methane. Can we draw the mechanism for the coronation of methane? So we have the initiation where the chlorine bond splits apart. We form two Cl radicals. The chlorine radical goes and grabs a hydrogen, abstracts a hydrogen off of the methane, so we get HCl and the new methyl radical. Then the methyl radical goes and abstracts a chlorine off of Cl2, so we form methyl chloride and a new chlorine radical. And then in the termination, any two free radicals can form the bond, so two chlorine radicals form Cl2, or two methyls form ethane. Doesn't matter what comes together because only a small amount happens here. So it could be two chlorines, a chlorine and a methyl, two methyls. It's easiest to normally draw just what was the initiator, what initiated the process, just reverse that. So the initiator was the chlorine bond homolytically cleaving, so the termination could just be two chlorines coming together to form, okay, just to keep it simple. All the products for the reaction must be formed in a propagation step, okay? So if it's not formed in a propagation step, it's not showing what's going on in the main portion of the reaction. The termination step is only if it happens once in a while, so you can't count on the product forming in that step, okay? So be careful about that. For the initiators, as I said a second ago, it's a bond that homolytically cleaves and normally is something that's symmetrical across that bond. So BR, the peroxide, the peracid, anhydride, whatever, they're the same thing on either side of it, so those are the easy things to split apart. Now, we've shown that the coronation of methane is possible. Is this reaction thermodynamically possible with bromine, fluorine, iodine, and chlorine? Okay, so if we look at all of these, we see that the ones that are most likely to happen are the HBr and the HCl. The iodine is very plus 55, and the fluorine is minus 431. And people don't like working with fluorine, so we'll stay away from it. Okay, and the iodine isn't very likely to occur. The one reaction that's most favorable and the one we can control the most with is the bromination. And the bromination is the one that we'll do the vast majority of, because with the bromination, it's selective in how it reacts, and it's going to go primarily to the most stable radical. Okay, so in this, where we have propane, if we react it with bromine or chlorine, we run the possibility of forming two products: one, the 1 halo, and the 2 halo. Okay, now we already have said that the more substituted the radical is, the more stable it is. So the 2 halo compound should be the one that's more favorable. Chlorine is so reactive, you get a little bit more of the 2 chloral than the 1 chloral, but it's a 60-40 mix, so there's a lot of both of them formed. Okay, so it's not very selective in that, even though we have two hydrogens to take off of the secondary one, we have 6 that we can take off of the primary one. So there's a lot more hydrogens that could be removed to give us the 1 chloral compound out of that. And that's why we get so much of it in the reaction. But if we switch to bromine, it's actually a 97-3 of the secondary bromine to the primary bromine. So it's much more selective to go to the more stable radical because it's not as reactive. Okay. If we compare the chlorination of 2-methyl propane and the bromination of 2-methyl propane, the chlorination goes 72-28, so it's a little better than the 60-40, but there's still 28% where the chlorine goes where we don't want it. So that's almost a third of it is stuff we wouldn't want in this reaction. Whereas if we brominate it, 100% of the product we want is the one where the bromine goes to the tertiary carbon. So bromine is much more selective than the chlorine. So if we have the choice, we will go with the bromination over the chlorination. So here's the selectivity of things. Fluorine 1 to 1.2 to 1.4, not very selective. It gives a big bunch of everything. Chlorine is 1 to 3.9 to 5.1 from a primary to secondary to a tertiary carbon. A little more selective, but not very good. And then bromine 1 to 82 to a secondary carbon. So for every 83 compounds, one of them goes on the primary, 82 of them would go on that one, the secondary, and the tertiary one 1600. So it's why it ends up being on the tertiary carbon we just showed with the selectivity it is. Okay, then if we started with cyclohexene, the most favorable radical we can form is not where we add to the double bond, but where we remove the hydrogen on the allylic position. And we all know that we can draw resonance structures for this allyl radical by sending the electrons down and getting that resonance structure of it. And anytime we can show resonance structures, it's much more stable. So if we have a double bond and we brominate it, we will brominate it at the position next to the double bond. We will not react with the double bond. Radical additions to HBr, we'll touch on this for hair right now, and then when we get into chapter 8 later on, this will be one of the reactions we'll do a lot of when we get there, okay? But in an ionic reaction, the bromine goes to the more substituted carbon because the pi bond is the nucleophile. It attacks the hydrogen. You kick off a bromine. It gives a cation on the more substituted carbon, and then the bromine adds to that to give us the 1-bromo 1-methyl cyclohexane. So it goes on the carbon that's most stable for the cation. In the next one, where we have HBr in a peroxide, the peroxide is the initiator. It splits apart to form two RO radicals. The RO radical is going to react with an HBr, and it's going to abstract a hydrogen off of HBr to form a new radical along with ROH plus bromine radical. The bromine radical is going to react with the double bond, adding to it to give us a new radical with bromine on the less substituted carbon, and then that new radical will react with HBr to abstract a hydrogen off of it to form the 2-bromo or 1-bromo 2-methyl cyclohexane. And then we have to terminate the reaction with two bromine radicals coming together to form Br2. So we have the initiation step, we have three propagation steps where we have to form all of our products in a propagation step, and then we have one termination step to kill off the reaction. Okay, so in this we always have to have one initiation, 2 or 3 propagation steps, and then the termination step. And we have to show all of that and make sure all of our products are formed in a propagation step. So radical polymerizations, we can form a polymer out of this with ethylene. We can polymerize it to make a polyethylene by starting the process. Okay, so if the initiator is just going to be the ROOR, split it apart to two RO radicals. Okay, what's that RO radical going to do? It's going to add to the pi bond. So make a new radical. This new radical can react with another pi bond to make a new radical, and we just keep adding on the chain for however long we want to until we get our polyethylene. And then we terminate the reaction with two free radicals coming together to form a small whole molecule. So halogenation is a synthetic technique. We're in organic chemistry. We're trying to learn to make new molecules, figure out how we can make things. It's all about what can we do with it. So we've shown we can coronate something and we can brominate something, and we've shown that the bromination is a much better reaction to do than the coronation. So if you need to do something to an alkane, the only thing we can do is brominate it. So for the mechanism of this, the first step, two bromines split apart to form two bromine free radicals. a bromine free radical will abstract a proton from, or abstract a hydrogen, excuse me, it's not a proton, from our 3-methyl pentane to make a small whole molecule, the HBr, along with our radical on that 3 carbon. Then that 3 carbon can react with more Br2 to form our product of the 3-methyl pentane plus a new bromine radical. And then, since we formed both of our products, the HBr and the 2-bromo-2-methyl pentane, we can react our bromine free radicals together to form Br2. Okay, so with an alkane, the mechanism is always the same, where we split the bromines apart, forming a free radical, abstract a proton, then the new radical on that carbon abstracts a bromine, and then we terminate the reaction. It's always these 4 steps if we start with an alkane. The only thing that's different is the alkane is different as to which one do we use. Okay, and then overall, we can do many different things with all of this. If we start with an alkane, because there are 2 things we can do to an alkane. We can burn it, and we can brominate it. Okay, if we burn it, we get carbon dioxide. We're not getting anywhere. If we brominate it, we put a bromine onto it on the most substituted carbon, and then that we can take on and we can cause it to eliminate to form an alkene, or we can do a substitution on it to form some other molecule by doing either an SN1 where we go through a cation, or an SN2 where we have direct displacement to give us a substituted product. Okay, so this right here is what we'll get into in chapter 6 and after test 2. Okay, when we get into the reactions, we'll really get into substitutions and eliminations, whether it's SN1, SN2, E1, or E2. And don't worry about those right now. We'll worry about those after test 2. Okay, so have a good day. If you have any questions about this, send me an email, ask in class, and we can talk about it to make sure everything makes perfect sense. Have a great afternoon.